Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Before we dive deep into the world of mineral reactions, let's take a step back and briefly overview what we'll be covering in this lecture. Our journey begins with an introduction to mineral reactions. Here we'll explore the fascinating interplay of minerals and their importance to our world. Next, we'll delve into how minerals interact with condensed phases. This interaction is not just a simple game of mix and match. It's a complex dance that can have profound implications for our understanding of the natural world. Our journey continues with the formation of solid solutions. These aren't your everyday solutions. They're unique in their composition and can tell us much about the processes that shape our planet. We'll then explore the intriguing world of mixed volatile equilibria. It's here that things start to get really interesting. This is where we'll see how different elements can coexist in a delicate balance, creating a dynamic and ever-changing environment. Finally, we'll look at the role of thermobarometry in understanding the conditions under which minerals form. This is like the detective work of mineralogy, piecing together clues to tell the story of our planet's history. With this overview, you're all set to delve into the fascinating world of mineral reactions. So buckle up, because we're about to embark on a thrilling journey into the heart of our planet. Welcome to the world of mineralogy. Ever wondered how minerals react with different phases? How do they form solid solutions or interact with volatile equilibria? Well, you're not alone. These are questions that have piqued the curiosity of scientists for centuries, and they've given rise to a fascinating field of study known as mineralogy. In this field, we delve into mineral reactions, exploring how they interact with condensed phases, form solid solutions, and influence mixed volatile equilibria. Now, those might seem like a mouthful of jargon, but don't worry, we're going to break them down into bite-sized, digestible pieces that will make these complex concepts feel like a breeze. We're embarking on a journey to understand the very essence of our planet, the minerals that shape our world. So, grab your explorer's hat, because we're about to dive deep into the world of mineral reactions. Stay tuned to understand these intriguing processes in detail. Dive into the world of mineral reactions and learn how they interact with condensed phases. When we talk about mineral reactions with condensed phases, we're delving into the realm of geochemistry. Here, the interactions between minerals and condensed phases, that is, solids and liquids, are pivotal to understanding the formation and transformation of rocks and minerals on our planet. Let's break it down. Minerals, the building blocks of rocks, are made up of various elements. These elements are not static. They react, they change, they interact with their surroundings. And it's these interactions with condensed phases that can lead to new minerals forming. So how does this happen? Well, imagine a mineral in a solid state. When it comes into contact with a liquid phase, say molten rock or water, reactions can occur. These reactions can cause the mineral to dissolve, to change, or to form anew. But these reactions don't happen in a vacuum. They are influenced by a host of factors. Temperature and pressure, for example, play a key role. Higher temperatures can speed up reactions, while higher pressures can lead to the formation of different minerals. The composition of the condensed phase also matters. A water-rich liquid, for instance, will react differently with a mineral than a silica-rich molten rock. Another factor to consider is time. These reactions can take place over millions of years, gradually shaping the geological landscape as we know it. But they can also occur rapidly, in the blink of an eye, during volcanic eruptions or earthquakes. So whether we're looking at the towering peaks of a mountain range or the tiny grains of sand on a beach, we're seeing the results of mineral reactions with condensed phases. These reactions, driven by the intricate dance of elements, temperature, pressure, time and composition, are the silent architects of our world. Now, with an understanding of mineral reactions with condensed phases, it's time to move on to the formation of solid solutions. Ever heard of solid solutions? How do minerals form them? To start off, a solid solution is a solid-state mixture of two or more minerals that form a new, unique mineral structure. It's like mixing two different colors of Play-Doh together and getting a new color, but with minerals. Now, the formation of solid solutions involves a process called Substitution. Substitution is when one mineral takes the place of another in a mineral's crystal lattice structure. This can happen in two ways, by isomorphous substitution or by ionic substitution. In isomorphous substitution, a mineral replaces another mineral of the same size and charge. For example, in the mineral olivine, magnesium can be replaced by iron without changing the overall structure of the mineral. This substitution creates a range of compositions for olivine, from pure magnesium olivine to pure iron olivine, with many mixtures in between. On the other hand, ionic substitution occurs when a mineral replaces another mineral with a different size and charge. This often happens when the mineral is forming and the elements available can fit into the crystal structure. For example, in the mineral Plagioclase, sodium can replace calcium, creating a range of compositions. These substitutions are not random, they are influenced by the conditions under which the mineral forms, specifically the temperature and pressure. Higher temperatures and pressures allow for more substitution, leading to a greater range of solid solution compositions. So, why are solid solutions important? Well, they play a critical role in many geological phenomena. They are responsible for the variety of colors in gems and minerals, and they help geologists understand the conditions under which rocks form. They also play a role in the movement of elements through the Earth's crust, which can impact the formation of ore deposits. So there you have it. The formation of solid solutions is a fascinating process that reveals the intricate relationships between minerals and the environments in which they form. With solid solutions demystified, let's delve into the interaction of minerals with volatile equilibria. Now onto a fascinating topic, mixed volatile equilibria. How do minerals interact with it? Imagine taking a walk in a garden. You see a variety of flowers, each with their unique fragrance. The air you breathe in is a mix of these multiple fragrances, coexisting yet distinctly identifiable. This is quite similar to mixed volatile equilibria, which refers to the balance between different volatile substances within a system. In the grand scheme of geology, this system could be an entire planet, a volcanic magma chamber, or even a humble pebble. And the volatile substances, they are elements or compounds that can easily vaporize due to their low boiling points, such as water, carbon dioxide or sulfur dioxide. Now, how do our minerals fit into this picture? Minerals, the building blocks of rocks, interact with these volatile substances in fascinating ways. Picture a mineral-rich rock near a volcanic vent. The heat causes the volatile substances to vaporize, creating a high-pressure environment. This pressure, coupled with the heat, can cause the minerals in the rock to undergo chemical reactions. They may change their structure, combine with the volatile substances, or even transform into entirely new minerals. These reactions can tell us a lot about the conditions under which the rock was formed, but it's not just about the rocks. These interactions also impact the environment. For instance, when sulfur dioxide from a volcanic eruption reacts with minerals in the Earth's crust, it can produce sulfuric acid, a major contributor to acid rain. However, not all interactions are detrimental. Some minerals can act as buffers, maintaining the equilibrium by absorbing excess volatile substances. For instance, certain clay minerals can absorb large quantities of carbon dioxide, helping to mitigate the effects of global warming. So you see, mixed volatile equilibria is not just a theoretical concept. It's a dynamic process that shapes our world, from the rocks beneath our feet to the air we breathe, and even the climate we live in. Having explored mixed volatile equilibria, it's time to understand thermobarometry. Finally, let's explore thermobarometry, a critical tool for understanding mineral reactions. Thermobarometry is a technique used by geologists to determine the temperature and pressure conditions under which a rock or mineral formed. It's a bit like being a geological detective, piecing together clues from the past to solve the mystery of how a mineral came to be. Thermobarometry works by studying the equilibrium between different minerals. When minerals form, they do so under specific conditions of temperature and pressure. If we can understand the equilibrium between these minerals, we can reverse engineer the conditions that led to their formation. Imagine a group of actors on a stage. Each actor represents a different mineral, and their interactions represent the equilibrium between these minerals. By studying the script or the chemistry of the minerals, we can understand the stage setting where the play took place, or in our case, the temperature and pressure conditions of formation. However, it's not as simple as reading a script. Thermobarometry requires a deep understanding of the chemistry and physics that govern mineral reactions. It's a bit like understanding the language of the Earth, interpreting the complex chemical signals left behind by geological processes. One of the key aspects of thermobarometry is the concept of solid solutions. Minerals are not always pure substances. They can contain a mix of different elements. These solid solutions can give us valuable information about the conditions under which the minerals formed. For example, the mineral garnet often contains a mix of iron and magnesium. The ratio of these elements can tell us about the temperature and pressure conditions when the garnet formed. By studying this ratio, we can get an idea of the geological history of the rock in which the garnet is found. Thermobarometry is a vital tool in our geological toolkit, helping us unlock the secrets of the Earth's past. It's a window into the deep, hidden world beneath our feet, offering insights into the complex interplay of temperature, pressure, and chemistry that shapes the world around us. With this, we have covered all the topics. Let's summarize what we have learned. We have journeyed through the intriguing world of mineral reactions. What have we learned? We've uncovered how minerals interact with condensed phases, leading to fascinating changes in their structure and composition. We've delved into the formation of solid solutions, exploring how different minerals can coexist in a single solid phase. We then ventured into the realm of mixed volatile equilibria, understanding the balance of various volatile components in a mineral system. And lastly, we've demystified the science of thermobarometry, using this tool to measure the conditions under which minerals form. Collectively, these topics have given us deeper insights into the dynamic world of minerals. They've shown us how every rock, every mineral, holds a story of complex reactions and interactions. So, as we step out into the world, let's look at our surroundings with new eyes. Remember, every rock you see holds a story of mineral reactions. Keep exploring, keep learning. Thanks for watching us. Share our videos, subscribe our YouTube channel and press the bell icon and stay curious for new uploads.